5.1 Introducing the Second Law. So far we have learned about conservation of mass and the first law of thermodynamics, or conservation of energy. So any process must satisfy the conservation principles. So we formulated and applied the mass conservation and energy conservation principles for any closed systems or open systems. We are able to solve it for unknown values like work, heat transfer, or properties of a system. But these conservation principles cannot explain some thermodynamic processes. For example, we know that a hot coffee is cooled as the heat is transferred from the hot coffee to the cold surroundings. But we cannot explain why the reverse of the process cannot occur spontaneously. As the fluid in a tank is stirred by a rotating paddle wheel, the temperature of the fluid increases. If the wheel is stopped, the reverse of the process cannot occur. The thermal energy of the fluid is not expected to decrease and rotate the wheel in the opposite direction. So, things only occur in a certain direction. So here's another example. Let's say 100 kilojoule of thermal energy is provided to a heat engine. So how much heat can be converted to useful work? (100 kilojoule in ideal conditions? Or is there a theoretical limit on the work output? The first law cannot determine how much heat can be converted into work. So these phenomena cannot be explained by the conservation principles alone. So to answer these questions, we need to introduce the second law of thermodynamics. So in chapter 5, we study the second law of thermodynamics and a new thermodynamic property called entropy. The second law predicts the direction of processes, establishes conditions for equilibrium, determine the best theoretical performance of cycles, engines, and other devices. The second law evaluates quantitatively the factors that preclude attainment of the best theoretical performance level. So we can compare the real devices with these theoretical limitations. And the second law develops means for evaluating properties such as internal energy and enthalpy in terms of properties that are readily obtained experimentally. Now we are going to introduce the second law of thermodynamics. The second law of thermodynamics does not have a single statement to describe it. It can be stated in different ways. So we are going to introduce three statements that describe the second law of thermodynamics. First, Clausius' statement. It is impossible for any system to operate in such a way that sole result would be an energy transfer by heat transfer from a cooler to a hotter body. In other words, heat cannot be transferred from a low temperature to a high temperature on its own. For example, a cold coffee never gets hot by extracting the thermal energy from the colder surroundings. It is impossible for any system to transfer the heat from a cooler to a hotter body with no effect on the surroundings. A refrigerator removes heat from a refrigerated space that is low temperature and dumps the heat to the kitchen that is high temperature. This is not a spontaneous process, but the process is possible by providing work to the refrigeration system. Thermodynamic systems have heat interactions with the surroundings, known as a thermal energy reservoir. A thermal energy reservoir is an idealized body that has a relatively large energy capacity. It remains at a constant temperature regardless of the amount of heat loss or heat gain. It can absorb or provide large amount of heat without any change in temperature. So very large bodies such as oceans, lakes, rivers, or atmospheric air can be considered as a thermal reservoir. Thermal reservoir is also called a heat sink or heat source, depending on the direction of heat transfer. For example, an air conditioning system or refrigerator transfers thermal energy from a low temperature reservoir and rejects heat to a high temperature reservoir. Low temperature reservoir is the heat source, temperature T1, and the high temperature reservoir is the heat sink, temperature T2, and T2 is greater than T1. On the other hand, heat engine transfers thermal energy from a high temperature reservoir to a low temperature reservoir. In this case, the high temperature reservoir is the heat source, temperature T2, and the low temperature reservoir is a heat sink, temperature T1. So T2 is greater than T1. Kelvin-Planck statement. So it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. We need to introduce a concept of heat engine to explain the Kelvin-Planck statement. A heat engine is a continuously operating device that converts heat into work. A thermal energy from a high temperature reservoir is transferred to a heat engine. The heat engine converts a portion of the thermal energy to work, and it rejects the remaining thermal energy to a low temperature reservoir. A steam engine is an example of a heat engine. So it uses steam to produce mechanical work. So Kelvin-Planck statement suggests that no heat engine can have a thermal efficiency of 100%. That means we cannot make a heat engine that converts all thermal energy into equal amounts of work. So even an ideal heat engine with no energy loss due to friction cannot have a 100% efficiency. So some energy must be rejected to the surroundings in order to restore the engine to its original state. In other words, heat engine must interact with two thermal reservoirs, high temperature and low temperature reservoirs. Heat engines cannot interact with a single reservoir to complete a cycle. It will be easier to understand the statement using a water wheel analogy. The potential energy of the flowing water rotates the wheel. It will continue to rotate as long as the water is continuously supplied to the water wheel. But once the water passes through the wheel, it is useless. We are not using the water again that already left the wheel. The water after the wheel still has energy as it continues to flow, but we may not be able to bring it back to its original state to rotate the wheel. So we only use the potential energy difference between the initial and the final states. But we have to dump the fluid after it passes through the wheel. So back to the heat engine. Similarly, heat engines must reject heat to the surroundings to provide work continuously. That means heat input is always smaller than work output. This is the main idea of Kelvin-Planck statement. Both Clausius statement and Kelvin-Planck statements are negative statements. It is not possible to prove the statement. They are based on experimental observations. Also, the two statements appear to be different, but they are equivalent in the sense that a violation of either statement implies violation of the other statement. Entropy statement. It is impossible for any system to operate in a way that entropy is destroyed. The entropy of a reversible process remains constant, and the entropy of actual processes always increases. So we will talk more about this later after introducing the concept of entropy. Irreversible and reversible processes. A process is reversible when no irreversibilities are present within the system and its surroundings. Reversible process means that the system and the surroundings can be returned to their initial state. The process may be able to occur exactly the same, but in an opposite direction. It is like playing a video backwards. A reversible process does not occur in nature. It is an idealized concept. So all actual processes are irreversible. Process that is not reversible is called irreversible. So any actual process has some degree of irreversibility. And there are many factors that make an actual process irreversible. So here is a list of irreversibilities. Heat transfer through a finite temperature difference, unstrained expansion of a gas or liquid to a lower pressure. So when the partition is removed, the gas expands and fills the entire tank. Spontaneous chemical reaction, spontaneous mixing of matter at different composition or states. So consider two dissimilar gases are mixed when the partition is removed, or hot water and cold water are mixed. It cannot go back to the initial states. Friction. Sliding frictions as well as friction in the flow of fluids. So friction is present in all mechanical processes. Friction also occurs in fluids. When a fluid flows through a pipe, the shear force acts to the surface of the pipe. Electric current flow through a resistance, magnetizations or polarization with hysteresis, and inelastic deformation or plastic deformations of solids. So these processes are irreversible because they cannot be reversed without leaving a change in a system as well as the surroundings. Our interest usually lies in the system, not the surroundings. A process is called internally reversible if there are no irreversibility within the system. But there are irreversibility in the surroundings. For example, the quasi-equilibrium process we discussed before. A gas in a frictionless piston cylinder device is slowly expanded as the weight on the piston is removed gradually. It goes through a series of equilibrium states. Another example is a quasi-equilibrium heat transfer. In a closed system, a gas in the system is heated slowly so that it is always in equilibrium state. The surroundings of these systems experience some changes, but the system itself is irreversible. So we can say that they are internally irreversible processes. The internally reversible process is also an idealized concept to simplify an analysis.